and he will give you, our scope of the space weather work.
Good morning. Well, thank you, Hui. Thank you, Leslie. And I want to thank everybody in the organizing committee. Thanks everybody for coming. It's a great crowd. Thanks everybody online as well. I'm excited. This is actually a mini workshop we've been looking forward to for a long time, and it's finally happening. And we have actually a lot of different communities coming here together today. This is awesome. This is great. And I'll tell you my main expectation out of this is actually we come out with really better understanding who's doing what are everybody's plans, better understanding. I'm going to learn a lot. I'm coming from a terrestrial community, and so I'm going to learn a lot this week. And I think also what's really important is finding pathways for us to collaborate together and do more science, more discoveries, more innovation with that collaboration. So the goal of my talk here is to introduce you to JEDI. And I was told, to actually lay the grounds for, common vocabulary understanding on data assimilation, which is very complex. Not everybody is a data assimilation expert. So giving you a quick introduction about, JEDI and the JCSDA, the Joint Center, why it's important, what are the benefits. And I'm going to do all of this in one slide. So I've combined, I'll cheat a little bit with animations, but I'll combine this all in one slide that looks more like a poster, but it's basically a condensed sort of a cheat sheet about JEDI. And I hope that that'll be helpful throughout this workshop. So first of all, the JCSDA. So this is a collaboration between federal agencies. A lot are represented here today. We have NOAA, we have NASA, the Air Force, and the Navy. These are the core partners, and we have actually observers or associate partners with the Met Office in the UK and an SFNCAR. UCAR is also partnering in this. Our goal is to optimize and accelerate the use of satellite observations. We're basically not just satellite anymore. With any observation we can get our hands on, and we're really tackling pretty much all the domains of the Earth system, and hopefully, we'll expand to beyond the Earth at some points. Hopefully, we'll talk about this week. So let's dive into data assimilation. This is the one schematic about what data assimilation is. And by the way, feel free to interrupt for clarification or for any questions on the fly. I'm totally okay to have this as a dialogue. So the traditional schematic of data assimilation is basically, it's a big data problem that combines or blends or fuses, you can use different vocabulary, several sources of information. In fact, all the sources of information we can get our hands on. And traditionally, there's two major pieces. There are collective knowledge of the system that we're representing, and usually it's through numerical simulations, the model. So that model can be a physical model, dynamical model, based on laws of physics that humans have learned over centuries, or it can be a database model based on training through AI and machine learning, or it can be a hybrid version of these two. And then we anchor these simulations with observations, and these observations can be pretty much everything you can get your hands on. And they can be direct observation of the system or very indirect observations. It can be radiation that you perceive from a satellite of a particular variable on Earth, or they can be all sorts of things. And usually, that data assimilation software, it's actually a software, is actually quite complex. It involves complex solvers. It involves pretty complicated ways to represent errors, covariances of these errors, how to actually find sufficient balance for your model, how to make all sort of assumptions to keep things computationally efficient with a large dimensionality. So it's actually quite involved in terms of development, in terms of computing, in terms of maintenance. So that's one of the main motivation for the JEDI project I'll talk to about later. The product of the data simulation is the analysis, and that analysis is very often used as the starting point, the initial conditions for a forecast. So your numerical forecast is usually starting from something, and it's usually the output of the data simulation. So hence find that little button here. I'm not sure which one it is. Well, you'll see that bottom arrow, basically that cycles back from the analysis to the forecast. And so that's actually why we call it cycling, is because you have that sort of cycling iterations between this one here. Okay. Ooh, point at the screen. Doesn't matter. Thank you. So cycling between the model and the data simulation, and you ingest, you integrate, you assimilate your observations as you go. So initial conditions, one application for the data simulation, but you can also have climate. We have reanalysis for climate assessment. We have model development. This is a great way to look at issues in your model and iterate and develop new models. This is also a great way for training AI. Probably the best data sets right now for training our system AI is through this, and also for observation system design. If you want to launch the next greatest constellation of satellites, you might want to check what impact it's going to have, and data simulation is actually a great way to doing this. Just a quick citation in light blue here from a series of papers from Magnus et al. At ECMWF. They looked at terrestrial weather, medium-range weather forecasting, and found out that across different centers for numerical weather prediction, the strongest factor that was differentiating these were the initial conditions, and that's basically what data simulation is producing. All right, so that's the why, the data simulation. Now, what about the how? So first and foremost, JEDI, the Joint Effort for Data Simulation Integration, is a joint effort, as the acronym says. It's a consortium of jointness. It's a different way of doing our science jointly. And so it doesn't mean that everybody does the same thing, and at the end we have one thing that just everybody has to adopt. It means that basically we're trying to do things jointly first and have actually joint reusable capabilities that and then we can tune or customize, rather than do it the opposite way, where we do all things separately, and then you come in and have 10 different systems, and now you try to identify how they overlap, how you could collaborate more. So it's really pivoting to, let's try to do a lot of things together. We're like on the same bus together, and then the last mile might be very different because there's all sort of specificities. It's focusing on the next generation data simulation for a variety of applications. All these are in transit to operations right now in all these agencies, and also the private sector, and also a lot of collaborations are happening with academia and international agencies across various countries around the world. So this is really a unified approach, open source development, open science. How we do this is basically based on two principles. One is the separation of concern, and the other one is generic programming. When you combine these, you basically have a system that you can actually have mostly generic and reusable that can be then customized. So I'll explain a little bit this schematic here. On the left-hand side, you have your core capabilities. These are developed jointly, and these are generic algorithms. These are algorithms for data simulation, and they can be your solvers, they can be your representation of covariance errors in very large dimensionality, they can be your observation operators, they can be the way you do quality control, they can be all the nuts, nitty-gritty details of data simulation. And then you have various interfaces to a variety of models. We have more than 50 numerical models that are interfaced with JEDI. Interface with observations as well, different instruments. We have more than 60 instruments across, atmosphere, ocean, cryosphere, composition, and so forth. So this is a big software. It's about 1.6 million lines of code if you combine open source libraries and open source code that are on our repos. And in order to do this collaboratively, you need a lot of testing and automate that so that you can have a variety of contributions from a lot of different contributors around the world. So we have now probably more than a dozen pull requests on our software every day, 2,000 plus automated testing, and we've actually the system is portable. We've actually looked at least 20 platforms to, they're not all supported continuously, but they actually work there. The main thing is 97% of the code is reusable. When I say reusable, is when you actually start applying this for various applications, you don't need to reinvent the wheel. You basically reuse. So what's on the right-hand side now, that's a graphic here, is your test bed, where you take the code, have your data. Obviously, without data, you don't have data simulation, and you configure it or you customize it for a specific need. Now, are you interested in fire weather, or are you interested in hurricane prediction, or are you interested in sub-seasonal to seasonal forecasting, or are you interested in space weather? Which kind of space weather? So now you need to plug it with a specific model. So on the right-hand side here, these are examples for actually the specific case of NOAA with different models, but there are actually other a little longer lists of applications that are actively developed right now across agencies, for marine and land and pollution and climate and so forth. The bottom line is, on these right-hand side, these applications, we don't reinvent the wheel. 97% of that code is the same. You just customize it. So it's on the left-hand side, you have your generalist, and on the right-hand side, you have your specialist. It's like you train a really good flight pilot, and now you have a new plane model, and you just repurpose that knowledge into a very specialized case. So that's what we're aiming for with all of you today and in the future, is actually looking at all these specialized cases for the mesosphere, the thermosphere, magnetosphere, heliosphere, and understanding all the stuff that we can reuse. Some of it can be reused out of the box right away. Some of it needs to be adapted. That's why we have actually experts from all these fields in space weather, but also experts from the data simulation. So a decent chunk of developers from the JEDI project are here today, and here to help and understand the needs. And that's basically how we're gonna actually get the biggest bang for the buck. The biggest progress for this project is through customizing, redesigning, improving the design so that we make sure that everything that can be leveraged and reused is done that way, so that we don't reinvent the wheel. And that's a huge accelerator or multiplier for our needs. It's a multiplier for the development. It's also a huge multiplier for the maintenance, the transitional operations, the optimization, and future-proofing things, because there are a lot of some needs in the future, but we can't even know today. So having maximum flexibility is key. Last piece of the slide, then I'm done. So what? So what are the current benefits, the future benefits, the expected benefits? And I try to put this in 3 categories. on the research and innovation side, development. So community-driven innovation. So really what we're trying to get here is that convergence of efforts into JEDI is a vehicle for having multiple communities working on very different systems to actually come together and develop a data solution together and reuse all of this. What it means is it means a slightly different approach to what some of you might have done in the past, where you might, you used to own every line of code you were developing and everything that you did. Here, this is a lot more collaborative. That means that, when there's code coming in, we usually invite people to review code from different teams. So we're nurturing collective intelligence, having multiple points of view, look at the same features, so that we can have actually different perspective, and that usually comes with better solutions. In terms of ownership, it's also shared ownership, because now there's actually a lot of contributors to these, but that can be very very rewarding. We're really striving for modularity, so that it helps with the efficiency. The idea of separation of concerns is you can work on parts of the code and not have to worry too much about teleconnections with how it's going to affect something else. And an example is we have very clean interfaces to separate observations and models. In the past, when you were working on adding a new observation, you had to think about what is the model grid and things like this. In reality, you might be an expert in this new instrument, might not necessarily know all the models that might need that instrument. So that's we're trying to actually lower the bar of entry so that you can actually bring this in. And then interoperability and flexibility and customization. I've talked about it already. From an operation standpoint, scalability, performance is important. Accuracy, obviously, but also having portability to current machine, future machines. Portability is becoming a requirement rather than an afterthought, and future proofing as well. Now, in terms of the vision, and I'll finish with this, where we want to be, and I think this is sort of our general strategic goals. One is having world-class use of observations, working towards coupled systems. I'm sure there's a lot of interest to couple the whole atmosphere and beyond. So that's an opportunity, because together we have more resources than anyone else in the world. So I think we definitely can tackle this. Looking at really advanced algorithms, there's a huge avenue of opportunities with AI and hybridizing with data simulation. Continuous innovation and rapid transition operations. This is in the heart of the JCSDA. And finally, building, collective engagement and resilience. So that's, all these agencies are now really strategically involved with space, where we can rely on one another to support each other. And so you remove a lot of risks in terms of building systems. All right, I'm done with this, and thank you very much for your attention today.